Good afternoon, everyone, and welcome to Metal 2 Optimization and Debugging. As you know, we're talking a lot about Metal 2 this year with some of the great new enhancements to the platform, including GPU-driven rendering, machine learning acceleration, and on macOS, VR, and external GPU support. And not forgetting advanced optimization tools. So this afternoon, we're going to talk about the current Metal tools, give you a recap of those, talk about some great new enhancements to the Metal Frame Debugger, and then finally cover some major enhancements in terms of GPU profiling. But first, the Frame Debugger. So, hopefully you're all familiar with this tool. It's our fully featured Frame Debugger integrated into Xcode that lets you capture your Metal 2 work, be it compute or graphics, and then step through it in the debugger to inspect state and resources, letting you debug and optimize. One of our focuses this year has been on improving the performance of the Frame Debugger. And in particular, we've paid particular regard to improving the speed with which captures happen. And I'm happy to say that compared to Xcode 8, Xcode 9 now captures up to 10 times as fast, getting you from clicking the capture button to into the debugger much, much more quickly. As you'd expect, we have full support for all the new Metal 2 API, including raster order groups, sampler arrays, viewport arrays, and the new pixel and vertex array formats. One particular part of Metal 2 that we've paid a lot of attention to is the support for the new argument buffers. With this, in the buffer viewer, you can now see all the argument buffer arguments displayed in line. And you can click through, whether it be to a texture, sampler, buffer, or another argument buffer itself. We've also added support for VR captures this year, with automatic support for Steam VR. And we've added support for you to view your submitted surfaces in stereo. So when you get to the submit call where you're sending your surfaces off to the VR compositor, you'll be able to see left eye and right eye alongside each other to quickly spot any discrepancies. Another area of focus this year has been on improving the workflow for capturing more complex workloads. So now if you're doing compute-only work in Metal, or you're perhaps using multiple Metal queues, it's much easier to capture exactly the work that you want. We've added a lightweight capture API with some new Metal capture scope objects that you create at startup and then reuse every frame to surround the work that you want to capture. You'll see a demo of this later, but it's great for being able to, say, group all your regular rendering work in one scope and some asynchronous work like regenerating your tessellation factor buffers in another scope. And then when you come to capture, you get exactly what you want. We also have support for triggering captures programmatically from your app. We use this a lot within our test apps ourselves so that we can quickly do a gesture on the device and trigger a frame capture without having to switch our focus back to Xcode. Another new feature this year is support for Xcode's Quick Look support. So now you have lightweight Metal debugging in the CPU debugger. So if you hit a breakpoint, and there's a Metal texture there, we'll pull back the data from the Metal texture on the GPU and let you view it there and then. Similarly with buffers and samplers. This is great for those cases where a full frame capture might be too invasive. For instance, if you're debugging your resource loading or some other setup code. It's also great in cases where you're debugging some compute workloads as well. So last year, we introduced support for rich filtering throughout the Frame Debugger so that you could filter both on things like resource properties, but also within the Frame Navigator, you can filter based on contextual data. So what resources you're using at a given draw call will let that draw call show up. Well, we've taken this to the next level this year with support for data mining throughout your captured frame. So now, when you type, we'll give you context-aware autocomplete suggestions. And we'll now allow compound terms. So now, if you search for a given encoder, and then you search for a texture, we'll only show you autocomplete suggestions for the textures that are actually used within that encoder. One of our most requested features over the years has been support for pixel inspection. And we've finally caught up with that. So now you can do detailed inspection of individual pixels within your textures and your render targets. And if you have multiple attachments to your render targets, we'll show you the pixel values for the same location in each attachment at the same time. So it's really good if you're trying to debug what the color value is alongside depth and stencil and such like. It's also very valuable for debugging compute workloads if you're working with images there and you're, for instance, halfway through your CNN and you want to test see what the exact values in the buffers are. Another new feature we introduced last year was our vertex attribute viewer, where you could see all the vertex data as it goes into your vertex shader, shown on a per vertex basis. Well, this year we've added support for viewing the outputs from your vertex shader as well, and we'll display this in line with all your other input data. So, as in this case, you can see your position inputs and your position outputs at the same time. Well, to show you all these great new features in action, I'd like to invite my colleague Max to the stage, who's going to give you a demo of all this new stuff.
Hello, great to see you here today. I hope you're doing fine and you're hyped about Metal as we are. Xcode's GPU debugger helps you debugging your GPU and the Metal usage. I am Max, and I'm going to maximize your debugging experience showing our new features. Yeah, let me run my demo app. It is rendering a beautiful scenery with like snowy mountains, grass that is waving in the wind. And to make it even look nicer, I added some particles that are glowing in the air. But as you can see, the particles over the grass, there's some kind of a problem. So let's figure this out. As a first step, let's check if the texture is correct. Let me set a breakpoint in the rendering loop where this texture is being used. Hovering over a variable gives you access to Xcode's data types, and you can quick look into the texture data. This data is fetched live from the GPU, and it helps you to verify the resources you are binding. And of course, it works with all Metal resources. The texture in this case looks correct. So what else can we check? Our next step is to capture a frame. Using the little camera icon in the debug bar lets you capture a frame. But using a long press gives you access to capture scopes and command queues. A capture scope is one path through your rendering pipeline. Like my environment map, I'm only updating every couple of frames. In this case, however, we want to capture rendering. This is where the particles are being drawn. So let's capture this. And already done. For those who are not familiar with our tool, I will give you a quick run through all the views you are seeing here. On the left side, we have the debug navigator. It's a hierarchical representation of your frame. And we help you. We automatically group by command buffers and command encoders. But also your debugging groups are shown here, giving you fine-grained control over the grouping. You can select a draw call or any other Metal call to inspect further details. The editor in the center is showing the bound resources, all the Metal objects you are using in the selected API call. Again, you can see labeling your objects will greatly increase the readability, so I suggest to do that. The editor on the right side is showing the attachments, the output of the last issued draw call. So whenever you are navigating through your frame, you instantly see where you are. On the bottom, we have our variables view, where you can access all the states of each Metal object. Back to our problem with the particles. Here we can make use of our new super powerful filtering. So I know the particles are drawn somewhere in my forward rendering. So let me filter for this. Filtering for a command encoder will only show API calls inside this command encoder. Like this, but it's still a lot. So let me add an additional filter. We know it's using our particle texture. Filtering for a texture will only show draw calls using this texture. And boom. This combination of filters results in a single API call we want to inspect further. So let's go here. Let's take a look at the bound resources. The vertex attributes combine the data that is going into your vertex function and leaving it. Maybe we are doing something wrong with our geometry here. So let's open this by double-clicking. Let me also hide the attachments for a moment. Last year, we started to show you a nice layout for all the buffers. And this year, we added something more. In the header, you can see the direction where the data is flowing. And if we take a look, this is the output data, the data that is leaving the vertex function. This is the output position of every particle vertex. And as we can see here, there's no obvious error, like big numbers or something like this. So I assume this data is correct. So what else can we check? The debug navigator now gives you quick access to all the views related to this draw call. Let's switch back to the attachments again. We are using two render targets here, color and depth. Let's inspect some more pixel values. Using the Inspect Pixels button in the lower right corner, we'll present a new tool, a loop. This loop displays the value like they are outputted by the fragment function. And you can move the loop around all the render targets. But you can also use your arrow keys for pixel-precise control, even if you are not zoomed in. Also, you notice all the loops are being synchronized between all the render targets. That helps you to relate values. Let me find an interesting pixel now. Using a long press will instantly move the cursor. And here, we can see something strange. The depth value inside and outside a particle is different. And that's odd. Our particles shouldn't write into the depth buffer, of course. That will be an easy fix. And I'm also sure our new GPU debugger will help you fixing your issues with the GPU. I hope we see each other in the labs tomorrow morning or at the beer bash later today. Back to my colleague Seth.
So now on to GPU profiling. As you know, performance is crucial to games and other graphical applications, and achieving a consistent fast frame rate is always necessary. But on the flip side, you want to get the most out of the GPU for the best looking game as well, and at the same time increase efficiency for a longer gaming experience. Well, for all this, you need to use the GPU profiling tools. The first tool I want to talk about is Metal System Trace. This is our tool for investigating timing issues, by which I mean investigating cases where the CPU and the GPU might not be running in parallel because you have some syncing operations by mistake and you're forcing them to work in serial. It's also great for investigating those cases where you're mostly achieving the frame rate you want, but occasionally you get a stutter and you need to figure, OK, what's going wrong in that particular frame? It lets you trace your Metal workloads through the system, from CPU to GPU to display. This year, we've added support for VR applications with specific VR trace points for activities like when you query the headset for pose data, when you submit your surfaces to the VR compositor, when it does its work to do the compositing, and finally, when it hits the glass on the headset. In effect, it lets you trace from motion to photon. We've also added support this year for the new ProMotion displays, as you'll find in the new iPad Pros announced earlier this week, and also support for external GPUs on macOS. It's also worth noting there are some great improvements in the instruments to make it much easier to view other instruments alongside Metal System Trace in a more integrated fashion. Our next profiling tool is the GPU Shader Profiler, the tool for probing shader performance. It's integrated into the frame debugger and lets you view shader time on a per draw call and per pipeline basis. And if you're on iOS or tvOS, it also lets you view it on a per line basis. Well, our first new tool this year is designed to work hand in hand with the GPU shader profiler. We call that Metal Pipeline Statistics. Metal Pipeline Statistics gives you a direct line to the GPU compiler to find out about the quality of the machine code that the compiler is generating from your shader. Gives you a rich set of statistics with things such as instruction count, instruction mix, by which I mean the relative ratio of operations such as ALU or memory or control flow. And on GPUs where it's relevant, it'll also show you register usage and occupancy. For GPUs such as that, these measures are crucial in understanding what is the limitations on how many shaders can be scheduled simultaneously, by which shader instances can be scheduled simultaneously. But even better are the new compiler remarks. With this, the GPU compiler will give you direct, actionable guidance on the performance of your shader and things you can do to avoid performance hits from things such as slow mass usage, register spills, and stack usage. It's like having a GPU compiler engineer built into every Xcode. For each remark, it'll explain what it means, what you can do to reduce it, and give you a link to where you need to go to fix it. Well, to demo this new feature, I'd like to invite my colleague Jose to the stage to give you a tour of Metal Pipeline Statistics.
Hello, everyone. My name is Jose Enrique. I'm going to present you our new feature on our GPU Frame Debugger that will help you improve your shader code quality. As you can see, we're replaying a capture of Metal Deferred Lighting demo for iOS. The first thing I'm going to do is I'm going to change my Debug Navigator view from view frame by call to view frame by performance. What this view gives is all used pipelines in your capture sorted by time. Remember, in Metal, a shader is always linked to a pipeline. Therefore, this is also a list of all shader combinations that are available in your capture. I'm going to go to the pipeline statistics view of the most expensive pipeline to see if we can improve the shaders. As you can see, this view has 3 sections. On top, we have remarks. Remarks are a unique approach to compiler shader code quality, as they report final compiler code generation issues. Remember, the GPU will execute your shader millions of times per frame. Therefore, the better code generation you can get, the better the performance it will have. Remarks are also sorted by relevance, and if expanded, they offer you a reason on why we're reporting it and a recommendation on how to prevent it. Below remarks, we have an overview for each shader, where you can see how the compiler final assembly is composed, subdivided in several categories of instruction ratios. And finally, we have a list of all draw calls using this pipeline. This will become very handy whenever we're iterating over our shaders. So let me showcase an example of workflow for pipeline statistics. If we go to our top remark, register spill, we can see that the compiler is reporting a big spill, 1,040 bytes. Spills will cause the GPU to access memory, which can stall your shader execution. Knowing that the compiler is spilling and fixing it can drastically improve your shader performance. Yet finding where and why the compiler is spilling tends to be a time-consuming manual analysis. But notice the second and fourth remarks, dynamic stack store and dynamic stack load. If expanded, they offer a reason, and expensive stack load is emitted to a dynamic offset in a local array, as well as a recommendation to reduce the stack access, eliminate dynamic access to local arrays. What this is basically saying is that we have an array variable in our shader code that is stored on the stack, and we're accessing to it using some other index variable. This is a very common pattern when programming for the CPU, but GPUs are different. They suffer when we over-rely on stack usage. But note the line just below the recommendation. It has an exact line number. This means that we option-click to it, we'll jump directly into the shader code line where the compiler is actually loading data from the stack array. We just found the compiler spill. Also, this aligns very well with our shader profiling data, informing us of the high cost of this line, which now we know exactly why. This shader is doing two passes. A first pass doing some light computation, and a second pass doing the light accumulation. Let's fix this issue by working with the compiler, but from a GPU perspective. The first thing I'm going to do is I'm going to remove the stack array. I'm going to remove its initialization. And then I'm going to compute the light accumulation directly into the first loop. Then I'm going to remove the second loop, as it's not needed anymore. Now I click my Update Shader button and wait for the results. What this is going to do is going to help the compiler to perform whole loop optimizations, allowing him to reuse the same register over and over, instead of relying on the stack. Once the results are back, we can see the instruction ratio between the previous and current code generation has been reduced, as well as the impact of this change on every single draw call using the pipeline, giving us also whole trace performance improvements. And with this, I conclude my example of workflow for pipeline statistics. I hand it back to my colleague, Seth.
Thank you, Jose. And finally, on to our last new tool today, GPU counter-profiling. As you know, GPU architecture is complex. With a pipeline consisting of multiple programmable and fixed function blocks, bottlenecks can appear at any point within the pipeline, and often at multiple simultaneous points. Your job as Metal programmers is to minimize fixed function bottlenecks while efficiently harnessing programmable blocks. Well, to do that, our new GPU counter-profiling is a tool. It's integrated directly into the GPU Frame Debugger and gives you detailed GPU hardware performance statistics on a per draw call on macOS and per encoder on iOS and tvOS basis. And instead of giving you an arcane list of counters that change for every GPU and are hard to understand and often don't tell you what you need to know, we've defined a high-level set of counters that mean the same across each GPU. So you don't have a per GPU learning curve. So here is the counter profiler. On the left, we have the graph view showing you detailed GPU counter graphs, and on the right, the detail window. Let's talk about those in order. In the graph view, we show you counters across your frame, where the x-axis represents draw calls or encoders across time. At the top, we show you GPU time, as that's inherent to all GPU counter profiling. And then below that, a set of top-level counters that correspond to the stages in the GPU pipeline, along with some other top-level counters that correspond to shared execution units, such as the shader core and texture units. For each group, you can drill down to more detailed counters, exploring a lot more data for each stage. This is great for a workflow where you identify it as your first cut where you think the performance issue is, and then drill down to see why it's going on. In the detail view, we'll show you all the same counters from the counter graph view, but displayed in full detail numerically. And to give it context, we'll show it alongside the median, max, and total values for the frame as well. Now, both the graph view and the detail view support the same full, rich filtering options that we support elsewhere in the Frame Debugger. So if you want to just view certain pixel stats and certain memory stats at the same time, you can put together the search term and view everything you want alongside each other. But our highlight of GPU counter profiling is our advanced bottleneck analysis. With this, we take all the counters that have been pulled for each draw call or each encoder and perform rich analysis on it, both on a cross-platform basis and on a per GPU specific basis, to identify potential bottlenecks at each call. Alongside this, we'll give you lots of data about, okay, what's going on here, what could cause it, and an intuitive workflow to navigate direct to the affected area. Now, both all the bottlenecks and all the counters will have rich, detailed documentation within the Xcode docs explaining what each counter means in detail, why it might be a particularly high or particularly low, and what you can do about it. To give a demo of this great new GPU counter profiling feature, I'd like to invite my colleague Jose back to the stage to give you a demo of it in action.
Thank you, Seth. And hello again, everyone. This time, I will demonstrate our new GPU counters, a tool that will help you analyze your GPU performance. First, I'm going to replay the same demo that Max was debugging early on, but this time we will focus from a performance perspective. The first thing to notice is the new GPU gauge just under the API gauge. By clicking on it, we'll navigate to our GPU counter view. As you can see, there's a wealth of data here, available for the first time. With this view, you can now deeply profile any GPU performance issue that you have in any of your capture frames. So let me demonstrate how to find performance issues. First, let's focus on the graph view. As you can see, there's a main spike in GPU time at the very beginning of a capture. The first thing you want to do is to zoom in to see if there's a single draw call, there are more offenders. In order to do that, I can simply pinch and zoom, just like that. Any default system behaviors will work just as you expect them to. Now that we see that there's a main spike, we can click on this draw call to highlight its impact across all the pipeline. And hovering over each row will give us detailed information on how relevant that stage is for this particular draw call. In this case, vertex emission, vertex shader, and primitives do not seem to have relevant impact. On the contrary, fragment shader and pixels stored into a frame buffer seem to be quite high. Let's focus on the fragment shader first. If we expand this group, we now get access to a massive amount of contour data that gives us detailed information on what's going on in the shader stage. Glancing at these counters, we can quickly see that the stall time is unusually high, over 76%. This means that most of the time we're spending on the fragment shader is actually waiting for some memory or data to be available. This is caused because you are fetching from a buffer or from a texture, but texture caches should be hidden this latency. So let's go down to our texture unit to see what's the cache miss rate. And we can immediately see that the texture cache miss rate is also unusually high, almost 60%. This means that more than half of the texture samples we are doing are coming from video memory and not from the texture caches. Now that we have a better understanding of the issue at hand, let's focus on the assistant editor. As you can see, the assistant editors offer the same graph counter information as the graph view was offering, but this time display as a table view. But more important, look at the top. This is our bottleneck analysis tool. It will point out to relevant issues that we consider. It will analyze all the counters within the selected draw call and point out to any relevant issues that we consider important for you to pay attention to. In this case, highlighting the same as we just found manually by checking the graph, that the texture cache miss rate is high. When expanded, it also offers recommendations on what to check. In this case, check if sample texture have min-maps, and a quick navigation link to relevant views for this issue. For example, bound resources, where we can immediately see what's the issue at hand. We're fetching a 4K by 4K RGBA 32 floating point texture with no min-maps in both our vertex and our fragment shader. This is a 256 megabyte texture that is fetched all over the pipeline. No wonder we're trashing our cache. Just think for a moment what we just did. This was an incredibly detailed view on how GPU internals work. You finally have the data to prove what years of experience were telling you, that fetching from big texture is expensive, but now you know exactly why. Accessing this texture was a stall in the fragment shader because it had to fetch some data from video memory that was not available in the caches. This level of detail is typically not seen outside console tools. Solving this issue now, it's a matter of balancing performance, quality, and correctness. But I just have demonstrated how you can use GPU counters alongside the GPU Frame Debugger to help you investigate, analyze, and verify any capture information, any performance information that you have in your captures. And now I hand it back to my colleague Seth.
Thank you, Jose. So that's GPU counter profiling. Like all the new features we've talked about today, it's yours to enjoy in Xcode Beta 9, and it's available for all Metal-capable GPUs. You will find that more recent GPUs have more counters available due to the more modern nature of the GPU, but there's still a rich and very usable set available for all GPUs. However, we would love to hear feedback from you if you feel that there's particular counters that aren't exposed that would be particularly valuable. Please drop by the lab or file us a radar, and we'll be happy to investigate. So what have we talked about today? We've talked about some great enhancements to the Metal Frame Debugger with support for pixel inspection, inspecting vertex shader outputs, rich filtering, better capture support, better capture performance, and Xcode Metal Quick Looks. We've talked about support for debugging and profiling VR applications in Metal Frame Debugger and Metal System Trace. We've talked about Metal pipeline statistics, giving you a direct line to the GPU compiler for performance information. And we've introduced GPU counter profiling, giving you unheralded access to GPU performance counter data in Metal. For more information, check out the website. Our code is 607. I did want to call out a couple of other sessions. If you didn't catch either of the Introducing Metal 2 or VR with Metal 2 sessions that were on earlier this week, it's highly worth going and checking out the video. And in fact, even if you did see them, it's still worth checking out the videos. And coming up later this afternoon, there's a great session on using Metal 2 for compute in Grand Ballroom A at 4:10. And that's it. Thanks for coming. Have a great remainder of your WWDC 17, and enjoy the bash. Thank you.